Cool. Welcome everyone. And Today's presentation on SOLIDWORks MBD, and I'm also going to do some presentation on GD&T, which isn't a SolidWorks discipline. It's an engineering discipline, but share some information with that with you guys today. My name is Robert French. I'm an applications engineer, and if anybody has any questions about this, you can see my email there at the bottom. Feel free to email me. All right, cool. So let's talk about model-based definition, what MBD is. So MBD is, we're trying to eliminate the 2D drawing at this point. 2D drawings were good, they were sufficient, but there's a lot more information that can be gleaned out of a 3D model with rotatable and interactable dimensions and things like that. You can really get a lot more perspective on a part that is sometimes lost when you're reduced to a 2D format. So you'll notice the key word there in the definition for MBD for us is critical manufacturing data. So this isn't necessarily at a point in industry or just kind of in engineering where we can completely get rid of the 2D drawing. They still have a good purpose, they still have applications, but we're going to move some of the critical information, some of the more nuanced, hard to represent information into a 3D model, into a 3D view for manufacturing or communication purposes. All right, so let's talk about how we implement MBD. How would we go about using this functionality or using this style of workflow at our company? First thing we want to be sure to do is analyze the way our company uses PMI, product manufacturing information, right? How is this information being propagated and distributed through our own company and to additional vendors or customers and things like that? So if we look at kind of this workflow right here, where we look at 3D designs done in SolidWorks and 2D drawings, there's a huge delineation where you can go in a lot of different directions. This information can find itself in a lot of different aspects of our company. So, right, from marketing to bills of material, for sourcing and ERP, for manufacturing methods, whether it's CAM or inspection with like a CMM machine or a lot of different options. So the idea is we can kind of skip some steps here and use that raw original 3D design file and skip some other steps and get straight out to production or straight out to sourcing. Skip a couple of the intermediate steps that cost time and money and manpower. So all right, so understanding what the different jobs at our company is and what data is going to be need to be provided to them. So once again, just kind of a rehash of that last slide. Lots of different departments, they all have their different needs. Well, the idea here is if we can kind of link all of this back, if we can take all of this information and bring it back to the 3D model, back to this really comprehensive file format within SolidWorks, then it can save a lot of time and effort. All right, so understanding where we want to end up, understanding what's going to be useful where, what would be most efficient or pragmatic, uh, what's the best strategy for our company. So ASME has started to come out with this standard to help us understand different DCCs or data set classification codes. So where does our company fall? Where are we? You can see the two different categories here, 2D drawings and 3D models. Well, all the way on left is DCC1, where we're stuck in the old school. We're stuck in the 90s. We're only using these 2D drawings. That's the only deliverable type we have. And as we start to transition right towards DCC5, that's where we start to see everything push more towards the model, the 3D model, obviously model-based definition, that being the chief deliverable that we want to use. So understanding the little nuances and specifically what each DCC is important. The overall scheme is important. How are we representing data, how our manufacturing information rather. And so what we find most often is most industries, most of our customers find themselves in the DCC2 or DCC3 range. That's where 2D drawings are still pretty relevant, and you might see that jump into the 3D realm, that jump into MBD, uh, when it comes to CNC programming or CAM programming, right? A lot of CAM softwares out there are now utilizing uh, 3D geometry. They can interpret solid bodies and solid geometry, whether that's a SolidWorks file, an Inventor file, STEP, IGES, some of your more CAD agnostic, right? It doesn't matter what file format it is, sometimes called a dumb solid, just a geometry representation. Well, that's where we see most of the customers in that DCC2 or 3 range, where that 3D model is pretty much being used just to drive CNC and CAM programming, get some G code out. All right, so defining critical manufacturing dimensions. So one of the problems with the 3D model with just the dumb solid for CAM programming is all you have is that dumb solid. You've got nominal dimensions, but it doesn't take into account tolerancing or any other surface finishing, some of the more critical, nuanced, not as evident from a 3D model information, right? That stuff is typically found on the 2D drawing. So that's all doable in the 3D model with whatever version. You don't even need the SolidWorks MBD package. What the SolidWorks MBD package gets you is deliverable types, and I'll go over those inside the software here in a sec. But you already have the option, if you're dealing with another SolidWorks house, to put these dimensions right into 3D and really be clear in your manufacturing information. So in order to apply some of the more advanced stuff like GD and T, you might need some training, and I'm going to go over very briefly because it's quite an extensive subject. I'm going to go over briefly what GD and T means. What's a pretty simple application of it. Like I said, DIM Expert in SolidWorks, every version of SolidWorks has that. All MBD package gets you is deliverable types, but right now in SolidWorks, you could start learning right away about how to apply these things. You'll just be limited to dealing with other people that are in SolidWorks as well, that you have to deal with other SolidWorks users. So if you're trying to deal with people that don't have access to those file formats and things like that, then you're going to have to purchase the MBD package. We can provide a trial license for SolidWorks MBD for testing and see if it's something that fits in your wheelhouse. Uh, Also in the implementation of MBD, we need to talk about setting up 3D PDF templates. So one of the deliverable methods, one of the reasons MBD is very powerful is that we can spit out 3D PDFs, and basically anybody can open those, anybody with Adobe Reader, which is essentially everyone. So we'll go over very briefly how to set up templates so we can represent our information very clearly and create some documentation very quickly. And then this master 3D view creation and different views and things like that. That's once again kind of part of the DIM Expert and MBD functionality. I'll show examples of that in the software as well. And once you take all those steps, you can start rolling it out to your engineers, start to try to test this within your own workflow. So like I was saying, what MBD really gets you at the end of the day is the different deliverable methods. So SolidWorks models are great deliverables, but it's really only limited to other SolidWorks users or other SolidWorks houses. The 3D PDF is extremely strong. eDrawings is another great way to look at different files that we create here if you don't have a SolidWorks license where you can open the native files. And then lastly is the STEP AP242 format. It's a new STEP file format that can actually capture some of this critical or important PMI information from the model in a CAD agnostic way, right? In a way that doesn't require you and whoever you're dealing with to have the same CAD software. All right, so let's jump into the software real quick and take a look at an example. So here we have this little bracket arm where it's fully created, and this would be a part that we'd be ready to take to a 2D drawing, ready to throw some dimensions on there. So in order to avoid the 2D drawing, we're going to stay here with an MBD. You can see I have my SolidWorks MBD tab active, and MBD is an add-in, so it'd have to be activated in order to see this toolbar show up. But once we have the toolbar show up, we'll be working with these tools we see at the top. And the tab we kind of want to work in over here in the manager area where we're normally in the feature manager. we're going to go to the Dim Expert Manager. So this is where we'll start to see the different dimensions we add in the 3D view populate. We'll see a list of them here. So rather than do this manually, since this is a pretty simple part, I'm just going to use the auto dimensioning scheme uh, command within SolidWorks within MBD. So a couple options over here on the left in the property manager. We have what type of part we're dealing with, whether it's a prismatic or turned, right? It's essentially saying whether it's like an end mill or a lathe part. We have the tolerance type, whether we're just doing the kind of old school plus minus tolerancing or the geometric GD&T tolerancing. And I'm going to do plus minus for now, and obviously doing prismatic because this is a pretty obvious end mill part. And then we'll do plus minus for now because I don't want to jump into GD&T yet. And then you also have an option for pattern dimensioning. You kind of look at your parts, see how features are repeated. In this case, everything's pretty linear, so we'll stick with that. Right here, we're going to establish some datums. So datums I'll go over more in depth when it comes to GD&T. They have more of a significance there. Right here, when we're identifying datums, we're more so just identifying kind of 0 points, like an origin or G54 for maybe a machinist out there. Where are dimensions referenced from? Where are the critical kind of anchor features, if you will? In this particular case, I'm going to choose 3 different faces that are all kind of orthogonal to each other. What this provides me with, when I choose these orthogonal faces, now I've got one kind of in every direction or aligned with every principal plane. So all the dimensions I'll create as a result, I'll get all the dimensions that I would need. From vertical from this bottom face, horizontal from this right face, and depth-wise from this back face. Then I can dictate which features are important to me. All features, I can manually select ones, or I can just kind of do a generic class-based one. We'll leave everything where it's at. Go ahead and let the auto dimension scheme go for it. All right, now we see these dimensions showing up on screen. All right, so you'll notice the part changed color, and that's a result of the MBD functionality. And you essentially have a couple different color schemes. You'll have green for a face or feature that has been fully defined. It's adequately defined, satisfactory, not over or under. You'll see yellow for when it's underdefined. It's still lacking just a little bit of information. You'll see red for when it's overdefined. You've got too many things constraining that particular feature. And lastly, you'll see kind of the native part color and not constrained at all. There's just nothing going on with that particular face or feature. All right, so we did the automatic method. Now I'll show you just quickly how you can go ahead and say, oh, I want to add a additional location dimension. Click the 2 different faces, and for those that have used Dim Expert before, it used to be quite limited when it came to how you could select different faces or edges of the part in order to add these dimensions. With 2016 and 17 SolidWorks, they've really just alleviated a lot of the little nuances and awkwardness about selecting. You can select any face now, reference geometry like planes and axes, centers of mass. It's just opened up a lot more and a lot more intuitive and more akin to what you see in other parts of the software, which is a big part of SolidWorks in my mind. That similar tasks, similar selection methods are found in different places of the software. It makes it easier to learn and kind of pick up for people that have been around the software a lot, just not in a particular specific area of it. All right, so we continue to add these dimensions until we've got the part adequately defined to whatever we're trying to achieve. So these different dimensions are only relevant in certain views. So you'll notice when I rotate to this view right here, kind of looking straight on the part, any dimension that's going into or out of our screen is somewhat useless in this view. I don't know what faces those would reference. I don't know, what features they're pertaining to. You'll notice as I start to rotate the part to this perspective, we see those dimensions show up now in this view. So it's already starting to constrain dimensions to different orthogonal views that are relevant. We can take more of a arbitrary approach with that, and we can choose to capture 3D views manually and choose which dimensions show up in those views as well. So one of the views I already have pre-created is called this small hole. So if I zoom in, or if I activate small hole, it's zooming in and giving me a more in-depth perspective of this particular hole right here. I want this, zoomed in view to represent uh, the dimensions that are unique to this hole. I'm not worried about depth or overall height or anything, any other information. I want to represent in this view what is relevant to this tiny little hole and fully define it here. So this particular 3D view doesn't have any dimensions or note areas associated with it. That's why we don't see anything show up here. If I activate my main view, where I can see pretty much all my dimensions, they all kind of just defaulted here, I can find the different dimensions that are associated with that hole. So there's the kind of left to right dimension for it. Here's the overall height dimension for it, and here's the diameter for it. Those dimensions, or dim expert annotations, currently live in a annotation view that is not associated with my small hole view. The small hole view, if we mouse over it, uses the annotation view called small view. So I'll go ahead and right click these dimensions and say, add them to the small hole annotation view. You'll notice they'll disappear from here because they're no longer associated with this view. And after assigning them all over there, if I activate my small hole view down here, those three dimensions are now present because they live in the annotation view that I've associated with this 3D view. So let's create one from scratch, capture 3D view, what we're currently looking at. We'll recreate the small hole, we'll call it small hole example, for instance. And we're choosing the annotation views associated with that. These dimensions, once again, I know I'm repeating myself, but the language is a little repetitive. I just want to make sure I'm clear. These dimensions are associated with the annotation view called small hole. This 3D view is capturing that annotation view where those dimensions belong. So that's how we kind of organize and only put where dimensions that are relevant where they belong, right? Like I said, we can't, for instance, put a depth measurement on this current view into and out of the screen. It doesn't do us any good. It doesn't convey our part information very clearly or effectively. All right, so we go through all that, and once we've got all these 3D views created, uh, sure, it exists as its SOLIDWORKS part file, and that might be sufficient to send out to vendors or customers and things like that. But if your vendors and customers don't have SOLIDWORKS, MBD gives us these great other deliverable methods, and we can see kind of the options for those up here to the left of this kind of marker here, the separator marker. So we have the 5 different buttons over here for how do we spit out this information. So we have to publish the 3D PDF, and when we activate that, we have different templates, and I'll jump into those in a second, different templates that organize our information in different ways, a primary viewport, additional viewports, capturing custom property information, note areas, a lot of different things we can throw on those templates. We choose which views, the views we see listed here match the views we see listed here, match the ones we see down at the bottom under 3D views. We can attach additional files like inspection documents, approval forms, things like that. And then the one I really like that I think is really cool is the step 242. Once again, it's a dumb solid, but so it doesn't give the kind of feature tree history, how it was created in SOLIDWORKS, but it gives this important PMI information that's in the form of dim expert annotations. All right, so once we create all that, we can spit out the PDF. And I already have one created here, so save some time, just open the created one. So here's that same part. Up at the top, we see different notes and custom property information that was pulled in automatically from SOLIDWORKS. At the bottom, or in the middle, we have our primary viewport. At the bottom, we have all of our different additional 3D views that were created that we can activate simply by clicking on. So what's really powerful about this is this not just a 2D PDF. It is fully rotatable 3D. And in fact, it provides additional functionality such as clicking on dimensions and seeing the associated faces highlight as a result. So very clear conveying of product manufacturing information, right? It's very hard to misinterpret this as compared to a 2D drawing. All right, so let's look at the 3D PDF template editor real briefly. So we're adding primary viewports. We can add additional text boxes and things like that. Within these text boxes, we can link to a custom property field. We just have to make sure this custom property field would match a custom property in the SOLIDWORKS part name. So it's all about linking up your templates correctly. Once you set that up once, it should be pretty automated workflow. So you just add what you want, company logos. I copied this one off another customer's drawing. Just kind of inserted it as a JPEG, as a just another way of representing information. All right, so that's the template editor. And that's about it here as far as MBD goes. I do have a step 242 file that if anyone's interested that has e-drawings, I could send it to you, and you'd see that the step file within SolidWorks is just kind of a dumb solid, no feature tree history, but still has that dim expert annotations, things like GD&T and surface finish and some of the other information that's usually lost when you go to a CAD agnostic file type. All right, so that's it for MBD. Let's jump into GD&T very quickly. Ooh. Let me just skip through these slides real quick, guys. All right, so here we are at GD&T. So GD&T stands for geometric dimensioning and tolerancing. So it's a method of controlling feature forms and locations without using plus minus tolerancing. It's a little bit more in depth and advanced and can apply some more nuanced or more intricate controls. It's attempting to define nominal geometry, which in a lot of cases in GD&T has to assume theoretically perfect features, things that are perfectly pristine, the best virtual representation of that particular feature. So there's different standards when it comes to GD&T. There's an ISO and ASME, and there's mostly overlap between the two different standards. They just have a few different ways of representing and interpreting, but for the most part, fairly similar. Just realize that there are two different standards, so if you plan to practice it, make sure you're operating within the confines of each. And so GD&T will use what we call feature control frames and datums. We mentioned datums earlier. They're a little bit more in depth and a little bit more intricate when it comes to actual GD&T. All right, so let's review what feature control frames are briefly for GD&T. So this is a typical feature control frame. It'll have our leader line, which is pointing to the feature of interest, indicating which feature needs to operate within the confines of this tolerance. We have our geometric symbol. In this particular case, it's a perpendicularity symbol, but there's a whole swath of them. There's a lot of different types, from straightness, flatness, circularity, cylindricity, run out, profile of line, profile of surface. There's quite a big list. And so they all mean slightly different things. We definitely don't have enough time to cover all of them. I'm going to try to give you an example of one or two here. But just realize there's a lot of different ways we can control different shapes and things like that. We have the tolerance value listed as well. So this typically indicates some kind of range or location that our feature has to remain within or function within. And then lastly, we have datums. In this particular feature control frame, there's two datums listed, A and B. You can have up to as many as, really as many as you want, but you typically don't find over 3 on most parts. And once again, a datum can be a lot of different things. It can be a reference point, surface, or axis. And I kind of just generalize that into features, right? We're just talking about different locations on the part that we can grab, fixture to, zero on, right? Just kind of finding an anchor point or a 0 point from which to base other features. All right, so let's jump in, and I have 2 examples files that I actually created these. Ooh, let me see if I can get my Ooh, give me a sec, guys. Lagging on me a little bit. Ooh, come on. All right, there we go. So I actually used the MBD functionality to create this file set, using the MBD functionality within SolidWorks to explain how GD&T works. So they kind of go hand in hand. So it's kind of a cool way to represent it using, the tool itself to actually explain how the tool works. So this first part file I've created and hoping to create a series to explain a lot of the concepts of GD&T and hopefully roll this out to our customers at some point. This first one starts with defining a datum. So when we're measuring a datum, the datum is the 0 point. We need to represent that, use that to reference other parts to, or sorry, other features to. So the datum, as we can see above, is going to be this bottom surface of the part. So I went ahead and actually modeled the part unperfectly, unprismatically, right? When we deal in SolidWorks, the geometry we're creating is literally perfect, right? It's perfectly pristine. Uh, no part is ever made like that. There's no such thing as a perfect part. Nothing's ever perfectly flat or straight or any of that. So I actually went in with a deform command and added some inconsistencies to it. So how do we use that face or that feature, the bottom of that part now, as a datum? How do we reconcile the imperfections into, we're trying to locate parts to something or features to something that's imperfect. So how do we best go about that? So there's two different ways we can create or establish datums. One of the first ways is the old school granite block. So when we lie our part down on top of the granite block, it's going to rest itself on the three highest points of the three highest points of that plane on the bottom, and that establishes the datum. So essentially, that granite piece needs to be flatter than our part. And now we're essentially using that granite slab, the top of that granite slab, as our theoretical perfect datum from which we can reference other features. With some of the more advanced machinery and machines out there like CMM machines, coordinate measuring machines, we kind of measure datums in a different way. We're actually touching off on that surface with uh, a very accurate probe, and as a result, we create kind of a root mean square RMS theoretical datum that is a perfect average of all the high and low points. So in the case of the granite slab here, we're really establishing a datum offset from the part. It doesn't intersect the part, doesn't go through any of its features. Whereas with a CMM, we are finding an average of all the highs and low points and kind of drawing a theoretical or virtual plane through all those high and low points, an average in between them. So that establishes our datum. Now let's take a look at, a actual feature control frame. Uh, what is going on? Here we go. An actual feature control frame using GD&T. So we have our part here with a couple specifications on it. We have our simple plus minus tolerancing for the thickness of this part, but we also have a feature control frame that says we want to be parallel. That's the symbol for parallelism. The dimensional amount is 5 thou, right? And parallel to datum A being the bottom surface of this part. Ooh, that's why. Right, so we see all that right there. So, give me one sec, switch to this next step. All right, so just because we have GD&T on there doesn't mean we can ignore our dimensional limits. So since we had a ½ inch plus or minus 20 thou, our part still needs to live within the constraints of that ½ inch plus or minus 20 thou. So still has to have a thickness between 480 thou and 520 thou. So what does this start to mean? And I don't want to spend too long on this. If anybody's interested in these part files or getting their hands on these files I've created, go ahead and email me and I can send them to you. But real briefly, when we look here, once again, the dimensional reference planes that we see here, we still have to operate within those confines, but we have an additional constraint on this where these two other planes that are 5 thou apart, which is representing the parallelism GD&T callout, the feature control frame here, places two planes 5 thou apart, and those planes need to operate within the dimensional reference planes. Those two planes, those parallelism reference planes, are perfectly parallel to the perfectly virtual created datum that we measured on the bottom of this part, whether it was with the granite slab or the CMM. So a few things that can happen is if that bottom face happens to be a little askew or happens to be not quite perpendicular or lined up with our right and left sides of the parts, doesn't really matter. It's not trying to control those. It's trying to control the parallel reference planes. It's controlling that top and bottom surface with reference to each other only. So once again, I'm not trying to get too in depth because you can become really muddled and there's a lot more to it than this. But I'm just trying to give people a nice brief intro to the topic and just some of the general concepts that are usually associated with it. So one more actually that I'll jump into for us. Let me open it up real quick. There are some GD&T that don't even require a datum in order to control the part. And let me show you a example of that real quickly here, and then we'll call it. One sec, opening it up. All right. So in this particular case, we're just calling out for a flatness of this top surface. It has no reference to the bottom surface at all. It itself just needs to remain flat. So as a result, you can get these same kind of inconsistencies where, or kind of inconsistencies isn't the best word, but unique situations where as long as we're remaining within dimensional limits, this top surface can actually be at some skewed angle. I've obviously kind of accentuated that here. It's not quite to scale. I've just made it very obvious that as long as we're saying parallel or flat within 5 thou, all we're doing is controlling that top surface, saying that that top surface, the fluctuations in it, have to exist within that 5 thou gap. As long as that 5 thou window exists within our dimensional limits, we've satisfied the GD&T. We've satisfied that flatness call out. It's only once we start to introduce datums that we have to constrain these particular feature control frames, these particular features to some other feature or datum on the part. All right, so like I said, if anybody's interested in these part files or having a little bit more of a, I can give you a little bit more discussion or go a little bit more in depth or show you some additional resources where you can learn some of this information. Like I said, I plan to develop this this file set a little bit more and roll it out to our customers. But until then, I could provide you with other resources or have a quick chat with you about some of the more intricate parts about the GD&T. But go ahead and let me know. If anybody had any questions, Jose, just go ahead and let me know in the chat box. But that's all I got for you guys for today, and thanks for coming.